Hello students, welcome to another session of All 4 e-learning program. Now in this session we shall take up the applications of the electric field intensity due to a dipole on the axial line. In the previous episode we have evaluated the formula for the electric field on the axial line of a dipole. Now we will take the applications of it. So today's topic, applications of electric field intensity due to an electric dipole on its axial line. So before going to this, let's have a preview what we have learned in the earlier classes. So I was telling you, charge, a fundamental property of matter. Charge produces field. Field is a space where there are lines of force. The space around the charge where you feel the presence of the charge, that is electric field. Field intensity, it is the force experienced by a unit positive test charge. Right? We have evaluated the formula for the electric field due to a point charge, later due to multiple charges, even for a dipole. So for a dipole, we have calculated, like suppose if I consider a dipole like this, minus q plus q. If I consider a dipole minus q plus q, right? This minus q is at point A plus q is at point B. The midpoint of the dipole is O. The length of the dipole, this is A and this is also A. The length of the dipole L is 2A. Right? Now for this dipole, we have learned that dipole moment is length of the dipole into either of the charge, any one of the charge multiplied by the length of the dipole gives you electric dipole moment. So on the axial line of the dipole, axial line is the line joining the charges passing to the midpoint. The line joining the charges and passing to the midpoint. Now this is termed as axial line. On the axial line at a distance r, we have evaluated the formula for the electric field intensity. E is equal to 1 by 4 pi epsilon naught. It is 2 pr by r square minus a square whole square. This is the electric field intensity due to a dipole on the axial line of a dipole like this. Now this is for a dipole of considerable length. Suppose if I consider a short dipole. So I was telling you, an ideal dipole or a short dipole is the one which is the combination of two equal and opposite charges with charge magnitude being high, but the length of the dipole is very less, short, very small distance. So A is very less, but Q is high. So if I consider a short dipole, for a short dipole, you know the symbol is a bold arrow like this. For a short dipole of dipole moment P on the axial line at a distance r. So mathematically, what do I mean short dipole? Short dipole in the sense the length of the dipole A is very much less than r. It is very much less than the distance of the point of consideration. I am considering the point to be a distance r. Length of the dipole is A. A is very much less than r. So substituting this in this, we get, so the electric field due to a short dipole 1 by 4 pi epsilon naught, it is 2 pr by r square minus A is negligible, A is very small, so I neglected like this. So I get this as 2 pr by 4 pi epsilon naught, it is r square whole square, r power 4. So cancelling one of the r here, I get r cube. So therefore, for a short dipole, the electric field intensity is 1 by 4 pi epsilon naught 2p by r cube. The electric field intensity due to an electric dipole on the axial line of a dipole, for a short dipole, it is 2p by r cube. Magnitude wise, 1 by 4 is not 2 by r cube. Now how about the direction? Direction of the electric field at this point is parallel to the direction of the dipole moment. So P bar and E bar both lie in the same direction. So vectorially you can represent E bar as 1 by 4 pi epsilon naught, it's 2 p bar by r cube. This is the electric field intensity of a short electric dipole, right, at a point which is at a distance r from it. Now if I go deep into the analysis, mathematical analysis of this formula, so in various entrance examination, how the questions are being asked based on this, this will evaluate, okay. Now considering a dipole like this, a short dipole, remember a short dipole represented by a bold arrow on the axial line of the dipole at a distance r, I have calculated, I have derived the formula for the electric field intensity. It's 1 by 4 pi epsilon naught 2p by r cube. This is the formula. Now, on what factors does this electric field intensity depend? On what factors? Mathematically, if I compare. First, the electric field intensity is directly proportional to the dipole moment of the dipole, the strength of the dipole, how strong the dipole, the characteristic property of the dipole is measured by dipole moment of the dipole. Its strength is referred by P. The electric field intensity due to dipole also depends on P. So therefore, E directly proportional to P implies E1 by E2 is equal to P1 by P2. The more the dipole moment of the dipole, the stronger the field produced. It's purely directly proportional to it. The second factor, for the same dipole, now if I imagine two different points at different distance, now how does the electric field vary with the distance? The electric field intensity due to a dipole varies inversely with the cube of the distance. E directly proportional to 1 by r cube. This is called inverse cube law. Coulomb's law, force is inversely proportional to square of the distance. It's 1 by r square, but here it is 1 by r cube. It varies cube of the distance. So therefore, E1 by E2 is equal to, this is R2 cube by R1 cube. Or I can write this as E1 R1 cube is equal to E2 R2 cube. Electric field intensity due to a dipole. This is a very important point to note. Force varies with the distance by inverse square law. But electric field intensity varies with distance. For a dipole, for a short dipole, the electric field intensity varies with inverse cube law it is. So E proportional to 1 by R cube. It's E1 by E2 is R2 cube by R1 cube. Right? Next factor, third. Now when the dipole is in air, when I am placing it in air, then the electric field is 1 by 4 epsilon 2 p by r cube. Had this dipole been in a dielectric medium, a insulating medium, a medium of dielectric constant K, then we have learned in the earlier classes, the permittivity of the medium epsilon is K times the electrical permittivity of free space, epsilon naught. So when the dipole is in air, the electrical permittivity is epsilon naught. But had it been in a medium, then the electric field intensity in the medium will be 1 by 4 pi epsilon 2p by r cube. But you know epsilon is K epsilon naught. So if I substitute E is equal to here epsilon, for epsilon if I substitute K, it is epsilon naught K 2p by r cube. Now the electric field with the K, the dielectric constant of the medium. So the electric field intensity varies inversely with the dielectric constant of the medium K. K varies inversely with K. So the relation is E1 by E2 is K2 by K1, or E1 K1 is equal to E2 K2. So coming to the point, now putting all the three things in one single relation, if I put it in one single formula, then comparing the electric field for an electric dipole at two different dipoles at two different distances and in two different medium, then the electric field intensity according to the first relation, E1 by E2 is P1 by P2. So E1 by E2 is P1 by P2. Now with respect to dipole moment, right? Then with respect to distance, E1 by E2 is R2 cube by R1 cube. So it's into R2 cube by R1 cube. Into, now with respect to the medium, it is E1 by E2 is K2 by K1. It is into K2 by K1. This is the comparison of the electric field for two different dipoles at two different points in two different media. So E1 by E2 comparison. If the dipole moment is same, we will cancel this. We will get R2 cube by R1 cube into K2 by K1. If the dipoles are in same medium, K will be same. Distances, if you compare distances, with distance it is inverse cube law, a very important relation. It varies with inversely with the cube of the distance of the point of concentration on the axial line. Right? Ratio of the electric field at two different points under two different circumstances. E1 by E2 is K2 by K1 with respect to the medium, P1 by P2 for two different dipole moments, and R1 and R2 for two different distances. If we just even a bit inside into this, going keen into it, suppose if I consider a point on the axial line of a dipole, consider a short dipole P on the axial line of a dipole at a distance R, then the electric field is 1 by 4 pi epsilon naught 2p by r cube. Now what happens to the electric field intensity if the distance is doubled? Right? If the distance is doubled 2r, if I consider 2r, then E dash is 1 by 4 pi epsilon naught 2p by 2r whole cube. Now dividing this by this, dividing both this cancel 2. It is for the same dipole, P cancel. So E by E dash is 1 by r cube by 1 by this goes up. So it's 2r whole cube by r cube. It's initial by final. Final is E dash. Let us reciprocate. So E dash by E is r cube by 2 cube, 8 r cube. So therefore, at the double the distance point, at r it is E, then at 2r distance, E dash is equal to, it's E by 8. So that is E by 2 cube times. It reduces 8 times, it reduces 2 cube times. Had the distance been 3 times, 3r, then we would have got it as E dash is E by 27. Its E dash would be E by 3 cube it will be. Or if the distance is 4 times, 4 cube. So if the distance of the point on the axial line of a short dipole is made n times, if the distance is increased n times, then the electric field on the axial line is equal to, it becomes initial electric field at r, let us say it is E naught. If it is E naught, then it is E naught by n cube it is. If the distance is doubled, E naught by 2 cube, E naught by 8. If the distance is tripled, E naught by 3 cube, E naught by 27. If the distance is 4 times, E naught by 4 cube, 64, so on and so forth. So when the distance is increased n times, if the distance of the point is taken n times the initial distance, then the electric field reduces 1 by n cube times. Right? Similarly, if the distance is reduced to 1 by nth part, 1 by nth, reduced to 1 by nth of the initial distance, then E dash would be E naught by, then this is 1 by n whole cube. This will go up. So E dash will be n cube times E naught. Like if the distance is reduced to half, 1 by 2. So it's 1 by 2 whole cube, 2 cube, it's 8 times. Electric field becomes 8 times. If the distance is reduced to 1/3, it becomes 27 times. So on and so forth. So this way, the electric field on the axial line of a short dipole, is, if I change the distance from r to 2r n times, then the field reduces 1 by n cube times. Right? Now instead of taking it as a short dipole, had it been a bigger dipole, like a dipole with considerable distance between the charges, minus q plus q, and this is at a distance a and this is also at a distance a. Now I am considering a point to, let us say A at a distance r1. Then the field at the point at A, and there is another point B at a distance r2 from the center of the dipole. Now considering two different points on the axial line of a electric dipole of considerable length, not negligible length. It's not a short dipole. It is a bigger dipole with considerable separation between them. Then comparing the electric field. Electric field at point A, which is the distance r1, is 1 by 4 pi epsilon naught. You know, for a dipole of considerable length, that the electric field intensity is 2p into distance r by r1 square minus a square whole square. It's 2p, p is dipole moment, into r by r square minus a square whole square. Similarly, electric field at the second point where the distance is r2, it's 1 by 4 pi epsilon naught. It's 2p r2 by r2 square minus a square whole square. So comparing these two, EA and EB, divide. So this cancel. Since it is the same dipole, this get cancelled. So EA by EB is equal to this by this by this by this. This will go up and it comes down. It's r1 times r2 square minus a square whole square by r2. This r2 comes to denominator. r2 times r1 square minus a square whole square. So comparing the electric field at two different points at distance r and r2 for a dipole of considerable length. Earlier we were taking it as a short dipole. Now it is not a short dipole where the length is consideration or the distance of the point is considerable to the length of the dipole. Then it is EA by EB is r1 by r2 bracket r2 square minus a square r1 square minus a square. Now in this one, suppose if r1 and r2 very much greater than E, even from this also. So it's EA by EB is equal to, neglecting A here, you get r1 into, neglecting A, r2 square whole square, r2 power 4 by this is r2 into r1 square whole square, r1 square whole square, r1 power 4. So r1 will get cancelled as r1 cube, r2 gets cancelled as r2 cube. Again you get EA by EB is equal to r2 cube by r1. Same thing. Same as the earlier there. Okay. So for a short dipole it is like this. For a dipole of considerable length or the distance of the point considerable to the length of the dipole, then the ratio at two different points, very important question, mathematically a bit difficult to solve. You better remember the formula. So it's EA by EB, 2 points, r1 by r2 into r2 square minus a square whole square, r1 square minus a square whole square, right? Next. In one of the entrance examination, a question was asked like this. There are two charges minus q plus q. The separation between them is 2a. So this is a and this is a. Right? The length of the dipole is 2a. So from the midpoint on the axial line, from the midpoint, a charge capital Q is placed at a distance d, here at a point P. A charge capital Q is placed at a point P at a distance d from the center of the dipole. What is the force experienced by the charge Q placed at that point? Force experienced by the charge Q placed at that point, you can evaluate like this. So electric field at that point. What is the force at that point? Before finding the force, let me take the electric field on the axial line. We know for a dipole on the axial line, the formula is 1 by 4 pi epsilon naught. 1 by 4 pi epsilon naught, it's 2p into r by r square minus a square whole square. This is the actual formula, where P is the electric dipole moment of the dipole. But in this problem, we are not given with the dipole moment. The dipole moment P of this dipole is charge into distance of separation between them. So Q into 2A. This is the magnitude of the electric dipole moment of the electric dipole. So P is 2QA. R the distance D. D is the distance of the point. So R is equal to D. So substituting, the electric field at point P is 1 by 4 pi epsilon naught. It is 2. P electric dipole moment is 2QA into r, distance of the point D, by it is d square, r is d square minus a square whole square. D is d square minus a square whole square, like this. So therefore 1 by 4 epsilon 2 into 2qa into d by d square minus a square whole square. This is the electric field. Now at this point on the axial line of the electric dipole, a charge q is placed. Now what is the force experienced by this charge? We know according to the definition of electric field intensity is force experienced by charge q that is placed at that point. Now the charge placed at that point is capital Q. So cross multiplying, the force experienced here, the electric field is E. At a point where the electric field is E, if I place a charge capital Q, then the force experienced by it, F is equal to EQ. At a point where the electric field intensity is E, if I place a charge capital Q, then the force experienced by the charge, it is EQ. Now we have found the formula for the E at that point. So substituting force experienced by this charge is E, it is 1 by 4 pi epsilon naught. It's 1 by 4 pi epsilon naught 2 times of 2qa into d by the distance d square minus a square whole square into the charge that is placed at that point. The charge that is placed at that point is capital Q. So therefore the force F is equal to, it's 1 by 4 pi epsilon naught 2 into 2 4 a into d capital Q small q by d square minus a square whole square. D square minus a square whole square. So the force experienced by a charge capital Q placed at any point on the electric field at any point on the axial line of an electric dipole. So that force is 1 by 4 pi epsilon naught 4 times half the separation between the dipole A into distance of the point q1 q2 capital Q small q by d square minus a square whole square. Had this electric dipole been a short dipole, if it is a short dipole, had it been a short dipole, then in the sense the distance of separation is negligible when compared to distance of the point. So A is less than T. So neglecting A, you get the force F is equal to, it's 1 by 4 pi epsilon naught, it's 4AD capital Q small q by, I am neglecting A, so it is D power 4. Cancelling one of the distance. So force F is 1 by 4 pi epsilon naught 4A capital Q small q by D cube. When I cancel, I get D cube. Now this is the force experienced by the charge capital Q placed at any point on the axial line of electric dipole. It's 1 by 4 pi epsilon naught q1 q2 capital Q small q into 4A in the numerator by D cube. Now here this time force due to a dipole is inversely proportional to cube of the distance. Due to this dipole, the force is inversely proportional to cube of the distance, right? But according to Coulomb's inverse square law, when I was taking 2 point charges, force is inversely proportional to square of distance. Now for this reason, I wanted to show you that force due to a dipole, how does the force due to dipole vary with the distance on a charge at some distance? He is comparing, suppose if a point charge is placed, force due to this dipole, force due to this charge or on any charge, how does it vary with the distance? Due to a point charge on another point charge, force varies inversely to the square of the distance. But now, due to a dipole on a charge, point charge, then how does the force vary with the distance? Due to a dipole, instead of point charge, this is a dipole. And how does the force vary with the distance on the charge placed at a distance? Now that force varies inverse cube law. Now this is to be compared. Noted. You should remember thing. If the if you compare the force experienced by a charge, let's suppose this is the charge placed at a point. Force on this charge due to another point charge. If I am a point charge, force due to point charge, it varies inversely proportional to square of distance. But this time here in this case, he is asking the force on a charge, but not due to point charge. Now I am a dipole. So if due to dipole, what would be the force? How does the force vary with the distance? Due to the dipole, force varies inverse cube law. A very good thing to remember, right? Okay. Next, we were evaluating the electric field due to a dipole on the axial line of electric dipole on either sides of the electric dipole. But suppose if he is asking you to find the electric field at the midpoint of the dipole. Suppose there are two charges minus q plus q, right? Midpoint is O. This is at A, this is at B. This is at a distance A, this is at a distance A. We have been evaluating electric field due to electric dipole on the axial line of the dipole, on this side of the dipole nearer to the positive charge, and even on the other side nearer to negative charge. We have evaluated. The formula for the electric field is 1 by 4 pi epsilon naught 2 p d by d square minus a square whole square. For a point on the axial line of a dipole on either sides, whether on near to the positive charge or near to negative charge on the axial line. This is the formula. Now what would be the electric field intensity due to the dipole at the midpoint of the dipole here? Now this is to be evaluated carefully. Now we know, according to the definition of electric field intensity, it is the force experienced by a unit positive test charge. Whenever you are asked to find the electric field intensity, imagine a unit positive test charge. Let there be a charge Q naught, test charge Q naught at that point. We have to calculate the force. Then force by charge, F by Q naught is E. So let us find the force acting on the test charge, then find the electric field intensity at this point. Now, when I place a positive test charge on this one, now this is under the action of two charges. It's in the influence of two charges. So the positive charge of the dipole will repel this positive charge this side. The positive charge of the dipole repels the test charge in this direction. So this is the force due to positive charge. Now the negative charge of the dipole, N, it attracts this positive test charge this side, Fn. Both the forces are in the same direction. So the resultant force. So force due to positive charge due to this 1 by 4 pi epsilon naught small q naught by distance between them is a square towards left. Force due to negative charge 1 by 4 pi epsilon naught q naught by a square, same, and both are in same direction. So the resultant force is 1 by 4 pi epsilon naught, same magnitude. It's 2 small q naught by a square. Now we know, according to the definition of electric field strength, it is the force experienced by a unit positive test charge in the electric field. So the electric field is F by Q naught. F is 1 by 4 pi epsilon naught. Force due to positive charge is q naught by a square, negative charge q naught by a square. Same, adding both are in same direction. So the net force is 2. So it's 2 q naught by a square by q naught. And q naught cancel. So the electric field is 1 by 4 pi epsilon naught 2q by a square. A very beautiful question, right? Thank you. Oh yeah.